voltage, and you can pick that up with a resistive wall detector, but that's more for an instrumentation course. Then what you'll do is you'll get a voltage that's proportional to the current, the image current that goes along through time. So what you would see on an oscilloscope is you'd see the bunch pass you, and then when it comes back around again, you see it pass you again. And then the shape of this is basically the longitudinal shape of the bunch, if the bunch is going fast enough. If the bunch is very low relativistic, it'll have a fan due to it. So basically a bunch that's standing still, basically you really can't get much information on it because you just get the fan from the image charge that goes through that. But as you go through very fast, the fan gets smaller and it goes with this 1 over gamma. But I won't go through that. So now the bunch shape then you get is equal to f of t, where the integral of f of t dt is equal to 1. So we're going to normalize this. So then basically the beam current is going to be given by this thing where this is the charge in the bunch. That's the charge of an electron or a proton times the number of particles in the bunch times the shape. And it repeats every t rev from minus infinity to infinity. Okay, so since it's a periodic series in time, this means you can expand it in a periodic Fourier series. So if it's periodic in time, you can give it in terms of a Fourier series. And the Fourier series will be given by the revolution period, which is now turned over to revolution frequency, which is 2 pi over t rev. So this is kind of stuff that I'm assuming you might have seen somewhere before. If not, we can go through this in slower detail, maybe in the evening or something like that, over here or something like that. Okay, so then each one of these has these coefficients. These coefficients that are going to be given by the shape factor. So the coefficients and the shape factor are two things that kind of tell each other. If you know the shape factor in time, you can know the Fourier coefficients. If you know the Fourier coefficients, you can tell the shape factor. So the shape factor then is just given the integral of over the Fourier coefficient for each harmonic is just the shape factor integrated over the sine wave of that harmonic. And I'm assuming that you guys have seen this before, so basically you're just multiplying it by the sine wave of the harmonic, you integrate it, and that gives you the Fourier coefficient. Note that C0 is the DC beam current. All right, that's what you would measure for the DC beam current. And that f of t has to be a real function, right? You know, when you look at an oscilloscope, it's a real function. There's no complex values on your oscilloscope. That means then, if f of t is a real function, that c sub m and c sub, oops, there should be a minus sign, c sub minus m star are the complex conjugate are equals. Okay, so that you get a real function in the end. Because this guy here has to be real. Okay, so the next step is what happens then when you talk about these are periodic functions in time, but what happens then when you don't have a periodic function of time? And we're going to go to the limit between the two of them. For this thing is that a Fourier transform is the same as a Fourier series, except you have an infinite spectrum. You have an infinite spectrum of frequencies. With a Fourier series, you got them only showing up at every 1 over t rev. Now, if the machine got large enough for the LHC or something like this, then the frequencies get smaller and smaller, and they come or get closer and closer to each other, and they become more dense. And then eventually, in the limit of an infinitely sized ring, the Fourier series goes to a Fourier transform. So the Fourier transform is written here is that I of t is equal to some Fourier transform e to the j 2 pi f times t. Now you notice here, when you take a look at Fourier transforms, if a physicist was to do this, he would put in a minus I here. Electrical engineers will always do this. Now it's arbitrary because you don't live in the Fourier transform space. You live in the real world. So as long as it makes difference that you have the round trip, because here is the inverse Fourier transform, here's the Fourier transform, and basically the round trip, as long as this sign is opposite that sign, it doesn't make a difference. But those vector signal analyzers that we have in the room, they assume this sign convention, okay? And I'm not really want to stress this too much, but you got to make sure that you remember that these guys, electrical engineers, goes e to the j 2 pi f. All right, so now you can basically then pull the 2 pi out of here, so you can see that basically all you're doing, this Fourier coefficient, is just the sum of the weighted sum of at each frequency, and you sum that up, and that gives you your time dependence area. And then you get the 1 over 2 pi in front. Again, physicists will use 1 over square root of 2 pi. All right? That, again, doesn't make a difference, just as long as you go through the round trip is going to be 1 over 2 pi. But electrical engineers will always do it this way. They'll put the 1 over 2 pi in front on the Fourier transform and go to e to the j omega t. Those are the two key things to make a look at that thing. And you can see that the 2 pi cancels the 2 pi in here, and that adds over f, and that goes in f. So it's a very practical way of writing the Fourier transform. Then the inverse Fourier transforms I of omega, which is basically trying to get the frequency plane. That's just I of t e to the minus j omega t dt. Okay, so we're going to do a detour on delta functions. So you have I of t is given by this Fourier transform here, all right? But then this Fourier transform is also given by I of t. So you're just substituting one thing inside of the other, all right? So if you have I of t is equal to some, and let's expand this a little bit here. We can actually bring this guy t minus tau inside here. You can basically see that I of t is given by I of tau. The only thing that does that is a delta function, right? So if you have a function that returns itself, it's got to be the delta function as you do that. So basically here you can see the delta function, delta of t minus tau is 1 over 2 pi e to the j omega t minus tau over the integral. And you think about this, if you wanted to say, what does this mean? This means if I take two frequencies, okay, all right, if I take two frequencies and they're different and I average them over a very long period of time, okay, that's what I'm doing, or average them over the whole frequency period of time, they cancel out, right? They don't match, they don't overlap, except when the two frequencies are exactly the same. And then when I integrate over them, then they're going to actually get up to infinity. So this makes sense that this is a delta function. And this becomes really helpful. This little trick here is very helpful in terms of being able to do signal analysis. Okay, so your beam current, then your Fourier transfer, your beam current in the frequency domain, again, is given by this Fourier transform. And if you take a look at these two guys, that basically, you can take a look at the two guys here, and you can sit there that the Fourier, this guy here, this beam current of time is this Fourier series in here, and then therefore the Fourier transform of your beam current for a periodic signal is just going to be an infinite sum of frequency components. So I kind of went through this real quick. Okay, so this is the Fourier transform of the beam current over just one period. The shape of the beam current over one period. This is the Fourier series of that periodic series of the beam current, and that was an infinite series. So I can just substitute in basically this guy here, okay, into it. I'm looking for this. I'm looking for the Fourier transform. What do I see on a spectrum analyzer? Okay, and I know what IB of t is. It's a periodic Fourier series. So I put this guy into here, and this says that what I see on a spectrum analyzer for a periodic series is also a periodic series in frequency. Okay, so I thought I had a picture of that. Okay, so what you see on a spectrum analyzer, if you were to take a look at this resistive wall, on a spectrum analyzer, you'd see a bunch of peaks showing up at 1 over T ref. I thought I had a picture of this. Okay. So, but as you saw yesterday, spectrum analyzers, they don't measure currents and voltages. So if you took a look at this guy's units here, he's got units of amps times time, amp time, right? Or amps per hertz. Okay, that's his units. You didn't see that on top of your spectrum analyzers yesterday. You saw dBm on there. So spectrum analyzers don't measure currents and voltages. They measure the power deposited into a filter. Okay. So the total power into a spectrum analyzer, you would integrate the power density over frequency. So what spectrum analyzers really measure is not power per hertz. They measure power spectral density, okay? Which is power per hertz. Excuse me, I misspoke here. So what you're thinking about doing with the spectrum analyzer, you have that resolution bandwidth that slides across your screen. and measures the power in there, okay? And so what you're doing is so if you measure 1 milliwatt over a 1 kilohertz resolution bandwidth, then what you've measured at that point is 1 milliwatt per kilohertz power spectral density. That's what a spectrum analyzer is measuring. So you got to get this one really into your head. Spectrum analyzers measure power spectral density. The way it's implemented is that they take a local oscillator and they find out how much power is going into that filter. But the point of a spectrum analyzer is power spectral density. Okay, so how are we going to get this power spectral density? So the power spectral density, we have to take a look at time average power. So how do you look at time average power? You take the current squared, multiply it by the resistance and the termination of the analyzer, and you integrate that over some length of time, and you let that time go to infinity. That's the amount of power that's going into the spectrum analyzer. Okay, but since I of t can be written as a Fourier transform, and I of t is real, so you can write I of t here for this guy, and you can write I of t over here since it's real. You get the power into the analyzer is given by this nasty product, and you can work this all out. It's a lot of fun to do this, and there's about a few pages of algebra that you see that the power deposited into the spectrum analyzer is a limit as t goes to infinity, 1 over t, is Fourier transform squared d omega over 2 pi. And if you look back at that, then the power spectral density is given the limit as t goes to infinity, 1 over t, the magnitude of the Fourier transform of the current squared times resistance. This looks really weird, okay? This is not something that says, oh, no kidding. But it has the right units, right? Because this has units of amps times time. The time cancels, and this has the units of power per hertz. Actually, the time doesn't cancel because it's I squared. All right, so let's try to do something a little bit more practical. So I'm trying to show you when you get to this thing, how do you actually really, what does these things really mean when you measure the beam current? So when you go through these things, the reason why you want to do this, if you measure a beam signal, you can measure it in terms of watts coming into your resolution bandwidth, right? But what does that mean? How much beam current is it? Okay, what's the shape of the bunch? So you actually have to be able to go backwards to see what that means, because you get a real engineering number out of your detector, but you want to have a physics number, basically what's the beam current, what's the shape of the beam. So you remember go back that the beam current is the Fourier transform of the beam current is this infinite periodic series in the frequency space. That means then I just take, going backwards, and I'm sorry this is so spooky, I have to take this squared, magnitude squared. So you see that the power spectral density is two infinite sums and two delta functions. It doesn't get any worse than that, right? As far as really icky math. But there's some nice things. If you have one delta function and another delta function, if they're not on top of each other, they cancel. They never integrate. So infinity times infinity when they're not overlapped is 0. Right. Now, so then this leaves you with a delta function squared only over the sum of one set of harmonics. But the limit of 1 over t of a delta function squared, if you go through it, is just basically 1 over 2 pi times the delta function. Okay, so I've done some very quick, fancy Fourier math, but these are kind of useful tools that you should try to get in your toolbox. So I recommend that you go through this derivation and say, I get it, I know how to do this thing. Once you're able to do this, you can actually spend a lot of time being able to analyze beam signals in this. Okay, so that means then your power spectral density, and this is the cool formula that shows up, is basically just given by the Fourier coefficient squared, and it's given by a delta function at the revolution frequency, and you see that it shows up at every harmonic. So if I had just written this down, you wouldn't have believed me, okay? But this is basically the power spectral density. It's infinite at the revolution line. But your spectrum analyzers don't blow up, right? They don't go to infinity and blow up. They measure the power inside that band, inside that filter. The filter's wider than the delta function, so it's bounded. Right? So I like to get rid of the 2 pi's. I divide the 2 pi's out, and this looks like a very engineering number. This is what your spectrum analyzer has. It has delta functions at every revolution line, and it's given by the Fourier coefficient squared. So what does that look like on a picture? First of all, spectrum analyzers, you didn't see anybody do a negative frequency yesterday. Okay, it only does positive frequencies. That's because cosine is e to the j omega t plus e to the minus j omega t. Okay, so we can fold the frequency over. That means the DC component doesn't get folded over, but the other harmonics do get folded over. And you see that this is a function now from 1 to infinity instead of minus infinity to infinity. And this is what you would see on a spectrum analyzer based on that spectrum that you saw. You get this, you get the value at DC, and then at every FREV line, 2FREV, 3F line, you get 2R times the coefficient, the magnitude of the coefficient squared at each one of those lines. So by looking at the spectrum analyzer, you can go through this, if you knew your resistance, and knowing all these lines, you could determine your bunch shape, kinda. Because the problem is, you've lost all the phase information when you did this. So spectrum analyzers have a drawback in that because that spectrum analyzer just swept whenever it felt like it, right? You didn't tell it when to sweep, so you really can't get any phase information out of that. That's the nice thing about vector signal analyzers. Vector signal analyzers, you can trigger. So if you could trigger these guys on the clock of the RF system, then you can actually get the phase information back, but I won't go through that. But one of the things that's drawback is you lose all your phase information. The other thing that you got to realize, and this is an important thing when you guys start, for people who are calculating beam loading for RF systems, this is a thing that people always leave off. Here's the DC beam current. It's R C0 squared, right? It's R times the voltage squared. That's the beam current. That's the beam power. This is edge currents of I squared, and this is I squared R. This is the F revolution line. It's twice that. So when you do beam loading calculations, don't forget the factor of 2, or you're going to be short on your Klystron power. Okay, you got to make sure that you keep that factor of 2. I've seen lots of people drop that factor of 2 over the years, and it's an expensive mistake. Okay, and this used to be no big deal when people worried about copper Linux. Now with superconducting Linux and people really pushing very high-powered or high current intensity machines, this gets to be a big deal. Okay, so it's one thing to remember. Of course, the RF current is twice the DC current. Okay, so what's the power contained in each revolution line? At DC, you can see it's just the DC beam current, and at the other frequencies, it's 2 times this coefficient. Notice, though, for a couple things, is that if the bunch is really short, f of t is a delta function. Take the limit as the bunch goes very short. Then basically every harmonic is going to be the same. So if you look at an electron machine where the bunches are really short, then basically all the revolution lines should look exactly the same. They should all have the same amplitudes. For a proton machine where the bunches can be very long, let's say the completely full bucket, okay, and you have very long bunches, then you can see that you only see something at the revolution line and you see nothing for the other lines, okay? So they go from one case, from very long bunches, you should only see the revolution line, to electron machines where you see all the revolution lines, okay? So it depends on what type of machine you're doing. And this is important for people who are building diagnostics. I'll tell you the story that we have. I'm having a battle at ESS right now. Is we'd like to get everybody to help us and collaborate. So the first thing the instrumentation guys do is they sit there and say, hey, we'll go off to DAISY and use their button BPMs. And I said, that's an electron machine, guys. And they go, so what? I go, well, with an electron machine, the bunches are really short. It doesn't really make a difference. For a proton machine, the bunches are really long. So you need to build an appropriate detector on those kind of things. So just because you got a pal working on an electron machine doesn't mean you can pick up his equipment and bring it over to a proton machine. Okay, so that has to do with this form factor on this thing for building instrumentation. Okay, so let's just show how you can kind of use this as a piece of instrumentation. This is a poor man's bunch length monitor. So consider you have a square bunch with length toss of b. Okay, we don't have square bunches, but it makes the math easy. All right, we have a square bunch, and so therefore if the height is toss of b, then if the width is toss of b, the height has to be 1 over toss of b, and that's just the normalized thing. So when I integrate this, I get 1. So then I can do the power in spectral line n is given by the sampling function. Sampling function is sine x over x. The Fourier transform of a square wave is a sampling function called sine x over x. You're going to know this by the time you leave this class, that you will know Fourier transform of a square wave of sine x over x. Okay, so you see this guy here, this Fourier transform. So then let's plot that. You can plot then, if you took a look at the ratio between the first harmonic and the third harmonic. Okay, so here's the first harmonic, and here's the third harmonic. One has, well, let me put it this way. This is the ratio of harmonic n to harmonic n. So I can put in 1 here and 3 here. Okay? And then as a function of how long the bunch is, I could see that my third harmonic drops off the longer I have my bunch. Okay, so if I can make an assumption of what my bunch shape is, so I say it's a Gaussian, it's a square, okay, whatever I want to do, all I need to do is measure the ratio of the third harmonic to the first harmonic, or the fifth harmonic, or whatever harmonic you want to do, and then you could sit there and say, I know what the bunch length is. So this way you don't have to make, you can end up now, instead of making a bunch length detector that's very broadband, that's a hard thing to do, right? To make broadband signals, you're going to see this in this lab, that making broadband devices is really hard. Making narrowband devices is very easy, just as we saw with matching. So what you can end up doing is you can end up building yourself a detector that looks at one harmonic and a detector looking at another harmonic. You can calibrate those two guys, and then now you can build yourself a bunch length detector in which you can actually go off and see the bunches. If you really want to have a very high frequency bunch length detector, like an electron machine, you go to very high harmonics where you expect to see that go off. Instead of building these really fancy laser beamy things that people do, you can go back to the straightforward way of doing this and making a very well calibrated thing at a very high frequency, and you could build a bunch length detector that way. So in fact, one extra thing is just another thing to do is that you can actually use this technique for basically building yourself a quadrupole damping system in terms of, I probably should wait, I'll talk about that later, but this tells you about the bunch length. Looking at these harmonics, you can now sit there and see if your bunch beam is tumbling in its bucket, and you can take a look at this and use that as a way of tuning your RF system. Okay, so now let's go a little bit quicker. So let's sit there and say we have n bunches in the machine, they're equally spaced. Now these bunches are coming around m times faster, and now you have this 1 over m here, and this is not a hard thing to do. You go through this thing here, and then basically you find that everything that you see is that you see now things, instead of seeing, you don't see things at the revolution line anymore, you see it m times the revolution line. So that the bunches come around m times faster, they get spread out by m times longer in the frequency case. So this is one thing that's really thing to get in your head. If things are close together in time, they're far apart in frequency. It's just the opposite on things like that. So now you could see that the C0 coefficient is basically still the total DC current in the ring because there's M factor in there. It's still the total DC current in the beam. Okay, so now what you would see, for example, and here's the picture, here's one bunch in the ring. You see something that looks like this, okay, with all these little tiny bunches in here. For the same bunch here, okay, these are the same height bunches in here, but they're coming around m times faster. You still see that this thing is, now you can see this is n times bigger, but of course, because you have a lot more bunches in the machine, you expect that. It's still given by the DC beam current, but now you see this guy here is further apart and taller. Okay, a burst of bunches in the ring. We'll do this as, you'll do this as well. You have n bunches, they're separated, and then you have a dead space. So it would look like this on an oscilloscope. You'd have these bunches, dead space, bunches, dead space. So to do that, you don't want to do the Fourier transform of this. It's too hard to do both of them. You realize it's a combination of this times that. So I can do the Fourier transform of this and the Fourier transform of that and just multiply them together. So the Fourier transform of A of t is this. The Fourier where the coefficient C sub m is given by that f of tau function. The Fourier transform of the other guy is given by that sampling function because it's on, off, on, off. Okay, so you have this guy here, you get the sampling function, and now you've got an infinite set, you've got two sets of harmonics on here, so now you actually see every revolution line. Okay, before, when you had equally spaced bunches, you didn't see every revolution line, you only saw the RF lines. And now what you see is you see this modulated, this envelope being modulated by the bunch repetition pattern. Okay, so if this guy M, if this burst is small, okay, then you basically get to see this whole spectrum here, every line shows up. If this burst is long, okay, then you see only these lines show up. Okay, and so this is a way of taking a look at this. In most rings in which you have an abort gap, you will see things where you see this pattern showing up on this thing. So whenever you see an abort gap on a beam, you can see whether or not how your abort gap looks. Okay. So I'd recommend that you go through this again tonight with a glass of wine or beer and just try to see if you can do double delta functions with a couple glasses of wine in you, and let's go from there.
If you were actually, if you're monitoring the abort gap, you don't have enough dynamic range to use just this to see whether in fact the abort gap is actually starting to fill with particles.
Yeah, probably it's a DC current, so the frequency is low. So,
Yeah.
so what happens? So it's really not an abort gap monitor, in a way. It's more like an abort gap annoyance.
Yeah.
What happens is that the abort gap is DC signal.
Mm-hmm.
It's spread out there, so it has very low harmonic content on that. So you really can't do it. Where it really comes into case is in transient beam loading. Okay, so if you have this spectrum, this is the spectrum that goes through your cavities. Okay, and so normally with your RF lines, you would only really you have here basically this guy here. This is the beam current that goes through your cavity. So we'll talk about this later on when we have to talk about cavities. But you not only have your generator going into your cavity, you have the beam that goes through the cavity, and it leaves a wake in there. So the beam acts back on the next beam behind itself, and you have to take that into account. So that's outside the scope of this class, but that's called beam loading. If you have this case here where the beam is equally filled, you don't have transient beam loading. You basically just have steady state beam loading that goes on that thing. So this is a nice thing to handle, right? And the cavity impedance, you only have to worry the cavity impedance is over here. You don't have to worry about this line causing any havoc. When you get this spectrum here, now you got some problems. So this guy here is your cavity sits here, and not only does he see this line, but he sees the next lines next to him. And that's due to this abort gap. So that's what's called transient beam loading. And this was a huge deal for the PEP2B factory. Yeah.
So why do we get the high amplitude of the Fourier coefficient?
That's given by how this divot here that you get is given by what the shape of that gap. If the gap there's hardly any gap in there at all, okay, then this divot you would only see these revolution lines because it would look like a equally spaced machine, right? If you get this big abort burst and nothing else in there, you really get this accentuated abort gap here in which you would get all the revolution lines here. This guy here would start to, as the abort gap gets wider and wider, these guys start coming out like this. And you start seeing all the revolution lines into the point where you only get one bunch. Your abort gap is big and there's hardly any bunches. Then you see all the revolution lines. Right? Okay, so the problem that you're going to get though is, and going back, is that these two lines then go through your cavity, go through the cavity bandwidth. And then that means that they'll leave wakes in the cavity that'll beat up behind it. And the thing that you actually see is kind of like the tail wagging the dog. The front part of the backs looks really nice. The backs get kind of whacked around by the front guys, okay? Because there's a transient on it and there's an abort gap. that comes through and they get tracked on that. So one of the things that people had to do is they had to build very clever RF systems for transient feedback systems that were done in the PEP-2 beam factory. Probably one of the biggest things in high intensity synchrotrons was done for the PEP-2 B factory. Bell did it, the Japanese took a different approach. The Slack guys did probably what I consider probably the more clever approach. Bell just basically said, we'll just make our cavities have very low R over Q, which we'll talk about later, and then we don't have that much transient beam loading. So this has, these spectrums have lots of implication in terms of design of RF systems. That's outside the scope of the class. Okay. Did I answer everybody's questions? Is that okay? All right. So Betatron motion. Okay, in Betatron motion, only one particle gets to be on the right orbit. Everybody else has to do, so any other guy, there's only one particle at one time that gets to be on the right orbit. Everybody else is a little bit outside or a little bit inside. Okay, so if you're on a little bit on the outside, what happens is you go through your quadrupole off center and you get a kick. Okay, and then you go through another quadrupole and you get a kick back. That's the whole point of the photo lattice that people put together, and that's the part of the accelerated physics class. So that means that the beam wanders in Betatron motion as you go through this thing. And of course you guys know that you can't have integer numbers of tune or rational numbers of tune and all that kind of stuff. But, okay, so basically the beam comes through and it wanders around. Now, you can put a pickup across there, a transverse pickup. And the way I'm going to model this transverse pickup, I'm going to have a plate on one side and a plate on the other side. The beam goes through here and it leaves image currents along the metal beam pipe, okay? The beam doesn't actually touch the plates, it leaves an image current. Here, it'll create a stronger image current on this side than it will on this side because it's closer. So I have to see a stronger signal. Then I can actually take the difference between these two signals. And how I can take the difference is usually we're going to have these things here called these hybrids here. There's a number of them here. There's a whole bunch of stuff here that I'll probably grab the wrong one. Something that looks like this is these difference mode hybrids. They can take the difference between two signals. Things like magic teas can take the difference between two signals. So you don't have to do this with digital stuff. You don't have to digitize it and just take you could actually do this analog, and it's better to do it analog, okay, than it is to do it digital. Well, that's a separate topic. And you take the difference of that signal that comes out. Now, the image current collected on the upper plate gets 1 plus 2y over d. So take a look at this. When y equals d over 2, this becomes 1 plus 1 divided by 2. That means that you get all the image current on the upper plate and none on the lower plate. And y is equal to minus d over 2. So this is just a simplified formula for a parallel plate pickup. That means that this difference mode voltage is going to be, there's a square root of 2 to conserve power here, is going to be given by the beam current times Z0 times this displacement y over d. So for a single particle ring, this beam current of a single particle is just given by this delta function, which we did the Fourier transform. So I'm just going to do a single particle. I'm not going to do bunch shape, but you could do bunch shapes if you'd like. Okay? But then remember that the particle is going through Betatron oscillations. So it has a closed orbit, and it has a Betatron amplitude, and then it wiggles around the machine given by the tune of the Betatron oscillation, and it has a Betatron phase. So if I put that in there, this is my voltage signal that I get in here. I get to the e to the j omega t things. That's because the particles are going around and around, okay? And then I get this cosine term on top of it, because this thing is, the particles are going on one side one time, they're on the other side the other time. So if I do all this expansion here, I basically get this thing, I get an n plus q line here, and an n minus q line over here, okay? Because I can take cosine and write this as e to the j omega t plus e to the minus j omega t. So I get an n plus q over here and an n minus q there. So the Parallel spectral density for a single particle, this is the carrier line, this is the revolution lines right here, okay? And that's just given by the closed orbit. The beam is off-center through the pickup, and it doesn't change. But what I get on the other sides, I get, because the particle is wiggling around the machine, I get an n minus q line and an n plus q line. And I have a picture, I hope, of that. Yep, I do. Okay, here's f rev. This is due to the closed orbit. And then basically, this guy is the n minus q, and this is the n plus q. Of course, this is only for the tune less than 0.5. If the tune was greater than 0.5, I can't tell which is which. They cross over each other. Okay? So one of the things you can't really tell about this thing is you can tell about the frequency of the wiggle. The only way to tell who's who is to have more than one BPM detector and compare the two of them. So basically you have to take a closed orbit on this, and this is how people determine, I won't go into the details, but basically you cannot distinguish the integer part of the tune. So if I'm looking at one pickup, I can't tell the integer part, but by looking at a bunch of pickups, okay, so if I sit there and I take the beam off center and I inject it in the machine, as it goes around the machine, it's going to go like this, all right? So what I do is I look at all the BPMs around there and I count the wiggles on the BPMs and I get my integer part, right? And in the Tevatron, they got the integer wrong the first time around. It's pretty amazing, right? You know, people did precision magnetic measurements and they built things very closely, and the accelerator physicists swear to God that they had this thing perfect, and they get the integer wrong, okay, when they came up with it. And so you got to get the integer right. It's a big deal. So it's important when you build your BPM system to make sure that you can actually see the wiggles on the first turn. Okay, so as you can see here, is that basically Betatron oscillations have the same spectrum as AM modulation. AM modulation is basically given by a carrier frequency, and then it has a carrier signal, which is 1 plus m cosine omega mt. So this is a slow frequency, this is a fast frequency. Okay, so omega m is the modulation frequency, omega c is the carrier frequency, and m is the modulation amplitude. So this is like your closed orbit term, this is like your Betatron oscillation term, here's your revolution frequency, here's your n minus q and your n plus q. So this is what we've talked about before. You guys should really just know this super straightforward. Cosine of a plus b is equal cosine a, cosine b, minus sine a and sine b. So therefore, you can rewrite this guy here, that this v of t is v cosine carrier t, m cosine omega carrier plus omega m, cosine omega carrier minus them. So you get the plus frequencies and the minus frequencies. So make sure you understand how to do this, because that's how you're going to figure out how mixers work, and that's how spectrum analyzers work. So what an AM signal looks like. It looks like basically you get the carrier line and you get the two AM sidebands that are spaced a modulation frequency apart. Okay, so what we're going to do is we're going to play with AM modulation to your blue in the face. We're going to change M, we're going to change omega C, we're going to change omega M, and it's so that you get this upside down left and right and so on to get there. So one of the things you should notice here is this 1/2 factor here. And so whenever you build an RF system, typically you do this down conversion like Ralph was talking about before. And right away, you lose 1/2 of the signal on your sidebar. So that's called a conversion loss, and 1/2 is 6 dB. So all mixers have a 6 dB conversion loss on this thing. So the last thing you want to do if you're building a sensitive system is put your mixer as your first element in the chain. Ralph will talk about this in noise. You don't put loss as your first element in the chain. And he'll go through that later on. But you'll see that this is the 6 dB conversion loss. Okay, longitudinal motion. For single particle, now it goes under synchrotron oscillation. Instead of it going back and forth like this, it's wobbling back and forth in the RF bucket. Sometimes it's leading the RF, sometimes it's lagging the RF. So it's going back and forth in this. And it goes back and forth at the synchrotron frequency, and in the meantime, it's going around in the machine. So I've got two phases here. I've got the phase of the beat of the particle in the bucket, and I've got the phase of the particle as it goes around the machine. So the particle's longer, now instead of doing t anymore, because there's no real t to be looking at, I could sit there and say that this has to be a delta function in phi. Every time that particle has to come around 2 pi, I got to get a signal. I have no idea when that 2 pi is going to be, but I got to get a signal when that thing hits a 2 pi. Okay, so that's that's my Fourier series, or it's actually my periodic series in phi. Since it's a periodic series, I can write it into expand it into a Fourier series, except no longer in time. It's a Fourier series in phi. Okay, so here's my Fourier series in phi, in which I now have e to the j n phi instead of e to the j n omega t. Okay, but the longitudinal phase is a function of time, which it has omega rev t, and it's got the beam sloshing around in the bucket. Okay, here's the beam sloshing around, and this is the synchrotron frequency. This is the synchrotron amplitude right here. Here's the synchrotron phase, and here's the starting phase. So I write this thing up here, and now I have the really neat looking thing of an e to the sine, e to the j sine. Okay, so that is a disaster. Until you do complex variable theory. And then you get all the poles and zeros, and away you go. Some very smart man realized that e to the jz sine x is an infinite sum of Bessel functions, j sub m to z, e to the j mx. Okay? So to do this, go to any one of your favorite complex variable books, and you can figure out how to do it. I still can't figure out how to do it, but it's, okay, you can do it. All right, so anyway, so this now is nice because I got rid of that sine thing, and I'm now in the simple e to the j mx thing. That's a good thing, right? So now I can actually look at that in terms of the spectrum analyzer. But now I'm going to have an amplitude here, which is given by the Bessel functions. You got, here's J0, here's J1, here's J2, here's J3. So people get freaked out about Bessel functions. Don't get freaked out about Bessel functions. They're just like sines and cosines. You just know sines and cosines from 4th grade, but if we had lived in the cylindrical world, okay, you would always know how to do Bessel functions instead of sines and cosines functions. Okay, so there's no reason. You go to a book, you go to a computer, and they're just the same thing as a sine or a cosine. Okay, they just have an extra index onto them. So a couple things to know about the Bessel functions, just to remember that they do have zeros. They cross over to zeros. It's going to be a real fun thing to look at. J0 starts off here. J1 starts off linear. J2 starts off quadratic. J3 starts off as cubic, and so on and so on and so on. Okay. So, what you'll see now is this beam current is an infinite sum over the revolution lines, but now we have our infinite sum over the Bessel lines, and you can see now it's omega rev plus m omega s of t. So as you see right now, here's your revolution lines, and here now are surrounded by sidebands, which are given by, each one of these guys is given by the amplitude of the Bessel function. So the center line is given by J0, the two closest ones are J1, the next ones are J2s, the next are J3s. And as you can see, basically they drop off in amplitude if you're looking low enough frequency. Because you see right here, the J0 is the big guy, J1's next, J2's next. But if your modulation index is really big, that means your beam is really slamming back and forth in the bucket, you're going to be out here somewhere. Okay? But if your beam is hardly moving around in the bucket, you're going to be in this regime here. Okay? When the beam doesn't move around the bucket, you're like right here, and when it starts moving around the bucket. So now by looking at this, you can see how hard your beam is slapping around in the bucket. So you can get a measure of the synchrotron amplitude of that. Okay, so FM modulation. FM modulation has the same frequency spectrum as FM, or longitudinal oscillation is the same as FM or PM. And I like to think of really longitudinal oscillation as really PM. It's not FM. And there's just a 1 over omega issue. So for you guys, the difference between FM and PM is pretty much the same. Okay, it just depends on how you generate it. All right, so in FM modulation, you have a frequency, omega c plus omega m cosine omega st. So here's your phase modulation, okay, right here, and this is your carrier frequency here. Note that d phi dt is equal to omega. Okay, so if I integrate this, I have to integrate this thing here. I get phi as omega ct plus omega m over omega s sine omega st. Okay. So that v of t, given if my voltage is given by this cosine of a sine, you can see that it's given by an infinite sum of Bessel functions. Again, remember this has an e to the j omega t, e to the minus j omega t, so I get this infinite sum of Bessel functions here. So you can see that the first guy is J0 over, so this is the carrier frequency, this is the modulation frequency, not the modulation frequency, sorry. This is the carrier frequency, which doesn't show up here, that shows up here. The amplitude is given by the ratio of this guy to that guy. This is the rate at which things are slopping back and forth. This is how fast they're slopping back and forth, okay? So this is the rate, this is slop. This gets me confused all the time. You have to stare at it a lot, and you'll play with it. You'll play with the modulation frequency. So for FM, the modulation frequency is how loud you're singing, okay? The modulation amplitude is how loud you're singing. The pitch is given by your modulation frequency, okay? So think of it that way in terms of FM radio. Okay, but we did this for single particles. What we really want to do is talk about lots of different particles in a bucket, okay? Because what you're going to do is if you have one particle here, we worked it all out for a single particle, and we got this nasty formula here for a single particle, right? This is a single particle. But now we're going to have a collection of particles in longitudinal phase space, and this collection of particles isn't going to be a nice little function. It could be sloppy depending on what's been happened to it, its history. So in electron machines, it's really nice because synchrotron radiation absolves all sins. But in proton machines, you live with all the sins that you started off with at the beginning of the machine. They track you to the day you die. Okay, so here in a proton machine, you might get a really nasty looking thing. So anybody that's worked on the Fermilab booster has seen all sorts of icky, gooey stuff in there. So each particle, though, has a phase space coordinate. That means it's got a radius and it's got an angle in phase space. Phase space is its phase error and its energy error. So if all the particles were perfect, they would have no phase error, they'd have no energy error, and you'd have a single dot here. But all the particles have some phase error and some energy error, and you have some kind of distribution in phase space. Okay, so, but the thing about this, the density in phase space, they must be periodic in alpha with a periodic of 2 pi. If you go around in phase space one turn, you got to get back to the same answer. All right, so you can write that this thing is given, that your phase space distribution of R and alpha must be a periodic series of e to the jk alpha, okay? Because it has to come back around on itself. And the number of particles in phase space is just integrated by this. And again, we're going to do the same thing. This has to be real because phase space is a real function. It shows up real. So this is C of k is equal to C minus k star. And so the different values of k are the multiples, okay? Each one of these, remember, since the particle ran around in phase space at the synchrotron frequency, the whole distribution has to twist at the synchrotron frequency. So each one of the multiples will twist around at the same frequency. So here's the first one, this is the monopole, okay? It's boring because, well, it's not boring, it's a good thing, but basically it's just a circular thing, and it just spins around, and you can't see anything different about it. You just see it spinning around at omega s. There's nothing you can see on it. You don't see anything changing on it. The next one is probably the more interesting one, and the one you use the most. It's the dipole mode. The dipole mode has plus on this side, minus on this side, and it spins around. Quadrupole has the 2 loads on this. So this is a lot like if anybody's ever done antenna theory. Okay, the people basically talk about, there's a chapter in Jackson that I think it's like 16 that kills people, which is all the multiples. Okay, so you talk about all the multiple modes of a this is exactly the same thing. You go around in 2 pi, you sit there and say, well, why did you do all this stuff? The thing that's really nice about it, it shows up in the frequencies that you can actually analyze. You didn't have to do this multiple deconvolution. You could have stayed with just the distribution you started off with, but you can see now, this guy here really can't make any signal because nothing's moving. Even though it's moving, it's like pudding that's being stirred around. I can't tell one thing from the next. Here I can actually see things going around here. Here it's plus and minus on this side, and then it spins, and it'll be plus here, minus over here. So I can actually see something. So you can see that these guys here have a net charge of 0. This has a net charge of something. So you can never have something without a monopole. You always have to have the monopole term there. So what if you just had, by accident, somebody prepared it for you, that you had monopole and dipole prepared to your beam? That somebody had just put monopole and dipole prepared to your beam. You could deconvolve it, and let's say you'd have this distribution of this guy and this guy. Now, we live in the phase axis. Our resistive wall monitors look at phase. We can't see energy unless we're in dispersion, all right? But we can only see phase. So we look here, this is time. And now I add up here, there's more pluses on this side, there's minuses on this side, so it subtracts. So what I look like in time is I see the beam is over on this side of this side of the phase error, okay? Now, as this thing starts to spin, okay, it starts moving closer because the plus guys are getting closer, the minus guys here, it looks like the bunch is getting to the center until this guy lines up, this plus cancels this minus, and I'm just left with the monopole mode, okay? Now, as it spins over here, you can see it comes over here. So as you can see, this basically, the dipole oscillation looks like the beam moving back and forth, okay? So when you see the beam moving back and forth in the bucket, that's what people call a dipole oscillation because they're talking about the multimode, the dipole oscillation. And this moves back, since this spins at the synchrotron frequency, this oscillates at the synchrotron frequency. So, monopole distributions, quadrupole distributions. Now we have pluses on this side and minuses on this side. The pluses add weight out here, the minuses subtract weight out here, and they make a tubby bunch. Short on top, wide over here. When they rotate around, they make a skinny bunch because the minus guys slide over here and so on. But as you can see, the period between here and here is now twice the frequency because I can't tell the difference between this guy and, right? So it goes to twice the frequency. Yeah?
So, to re-observe the dipole oscillation, you have to move the observation point, right?
No. So you could sit there
No,
with,
but to just see the shape moving back and forth.
you have to have a trigger that's given by your RF frequency. So you know your RF, right? You know,
Yeah.
that's the thing. So you take an oscilloscope and you trigger it on the revolution frequency. And what you'll see on one turn, the revolution frequency is over here. On the next one, it's over here. It'll move. People build mountain range displays that are really cool. You'll see these things go back and forth like that. Okay.
So you're always thinking time domain.
Yeah, but in time domain, you do this. So you have to still trigger your signal. You have to get your analyzer to do this thing. So you in the time domain, if you want to see a mountain range, you will see that. In the frequency domain, you don't have to trigger. Because what you'll do is the frequency domain will start to see this thing moving back and forth on you. And what it will show up is, it will show up at, and I'll show you this in a second, okay? But it'll show, let me do a couple more slides. Okay, but you see, so we get this is a bunch length shape. The first one is a bunch centroid shape. A quadrupole is a bunch shape oscillation, okay? So if you see the bunch shape oscillating, you got quadrupole mode. If you get the bunch shape dipole, if you dipole, you have a bunch centroid mode. So if you're going to fix something, if you want to fix your dipole mode, how do you fix it? You have to shift the phase of the RF to catch up to it, right? You got to shift it back and forth. You have to make a damper to kind of, it's like, you know, catching it, and you have to kind of catch it and put it back into place. You know, you grab this bowl of Jell-O, and the bowl of Jell-O is going like this, and you got to kind of do this to it till it stops doing that, okay? So now, if you have a quadrupole mode, okay, how do you fix that? You got to change the amplitude of the RF, okay? So instead of doing this, you have to do this to get it in shape. So you have to change the amplitude of your RF. So this is important. So for example, when you see injections in the machines, if you see a dipole oscillation, the last thing you want to do is change the amplitude of the RF. You need to change the phase of the RF. Okay, if you see a quadrupole oscillation, the last thing you do is change the phase. You got to change your amplitude. And you look at this on the resistive wall monitors, and you can actually tune these things out quite nicely. Okay, so I'm sorry it's taking a little bit longer. So the total current is found by integration of the contribution over each particle in phase space. So we only did this for one particle right now, and so now we have to really integrate this all through. And so I went through, and remember now I have my nice little multipole distribution, C sub k. I put my C sub k in here, and now I have this frequency form factor, which has this J sub k times this f of r component here. And this f of r is basically the shape function of the radial shape function of the Fourier of the bunch shape here. I don't want to bore you guys too much before lunchtime, but you can go through the math there. But you modulate it by the J sub k. So what happens then is that now that each synchrotron line, because of this, all those other cross terms show out. So a quadrupole oscillation can't excite dipole modes. Just no way it can do that. A dipole oscillation can't excite quadrupole modes. They can only excite things at the synchrotron lines because of this integral that we just did. So what you'll see then on an oscilloscope in a resistive wall is you'll see the center line, that's the monopole line. If you take a look at these two lines over here, you see these two lines, those are the dipole lines. So if you saw these lines here and none of these lines here, you would tell that you only have a dipole oscillation. The beam is only going back and forth like this in the bucket. And that tells you what to do, all right? If you see just the quadrupole lines, but you don't see the dipole lines, you now know that you have a bunch-shaped oscillation, right? So this allows you people to build dampers that are specifically tuned to the multi-modes that you have. So at Fermilab, I know this because I built these guys, you'll have dipole dampers, basically, that look at the phase, and they look at the first synchrotron line. You got to design your filters right for the first synchrotron lines. The quadrupole dampers are built for the second synchrotron lines. These guys you use phase detectors to see. These guys you use bunch length detectors to see. Okay? And then you can actually go ahead and damp the lines that get excited. So, that is the end of the lecture. So this is really a gooey mathematical lecture. Don't have to worry about all the details, but just show you that there's quite a wealth of things you can do now with these spectrum analyzers in terms of analyzing things like bunch shape, motion of the beam, and analyzing what to do with the right shape of the beam is kind of key in doing this. Okay, so and you'll see a lot of this. We'll just do simple things where we put in AM modulation in there. You have to keep in your head, how does this work with the beam? FM modulation, how does this work with the beam? And you sit there and say, I understand FM modulation. It's really easy. Now I know what's going on. Okay, now we break for lunch. And we come back and
Yeah, so let's plan to be back at 1 o'clock. What I've been looking over the schedule is I'm going to take a half hour.